Hi, Jacob here. Today I'm going to be demoing a project I worked on with Connor, Johnny, Jonathan, and our advisor Helen Yu. The project we worked on was biometric identification with ECG signals, and this is basically just identifying a individual from their ECG signal. We identified people from their ECG signals with two methods, with an extreme learning machine and a convolutional neural network, and I'm just going to be quickly demoing the extreme learning machine portion of our project. So this is some of the code we wrote in MATLAB, and this portion of code is to read in the ECG signals, filter out some noise, and extract the features that will eventually go into the ELM. So I'm going to run this, and we can see the first ECG recording is here. And this is before filtering, and then afterwards, this is after it's filtered with the 3 cascaded FIR filters, and you can also see that we labeled the different peaks, the P, Q, R, S, and T peaks of the ECG signal. And then from these peaks, we're going to extract features for each heartbeat in this recording. So I'm going to remove this breakpoint, just run through this. We can actually see all the different recordings, ECG recordings popping up, being filtered, labeled, and then going through feature extraction. Okay, so I think it finished running, and we can see the training features we extracted to train our ELM, and every column here is 72 elements long, and that's because, like as I said, 72 features are extracted from each heartbeat. So every column here represents a different heartbeat within the recordings, and then we also have like labels that correspond to each column there, and this label just tells like what person that recording came from. So it's from person 1. Then we can see maybe like heartbeat, the features extracted from like heartbeat 83 are from person 2, and so on. And then we also have the same thing but for like testing features and labels. And this is these are features that will not be fed into the ELM for training. Instead, they'll be used afterwards just for testing. And we can go and run our ELM program over here. Alright, so we can see this GUI pops up, and we can see the kind of structure of our ELM, which is just 72 features are input here. There's a 22 neuron hidden layer, and there's a 5 neuron output layer, and this output is in just the one hot format, so we actually have to convert those labels earlier into a one hot format. And just to show quickly what that is we can look at the training labels again. So now instead of just being like saying 1 for person 1, instead it's going to be like 1 0 0 0 0 for person 1, and then for person 2 the second element is going to be high and the rest are going to be low. So that's just the one hot encoding that our ELM uses. And we can see the final results here in a confusion matrix. And as you can see, it did a really great job of classifying all the people correctly with the testing data. This was done with like this confusion matrix is created from the testing features and labels. So this is data that our ELM has never seen before, and it's just trying to predict features, like what what person those features belong to, even though it's never seen those samples before, and it manages to predict them with a really high accuracy of 99.3%. This varies slightly between runs. Like sometimes there'll be like a couple more mispredictions, so it might drop to like 98 or 97. But overall, those results are really good, and we can also go back and just check how it performed with the training features that it had been exposed to. And it's not really surprising that most of the time it manages to train, so it completely recognizes all people correctly with those training features. So that's also really good. And if you found this to be interesting, then maybe you'll consider reading our whole paper, which also talks about how we used a convolutional neural network for this same application. And thanks for watching.